Hey, my dear students, welcome back. In this video we are going to learn about carbohydrates, how to draw the Fischer projection, how to make cyclization of carbohydrates for aldoses and for ketoses, how to name them, what is D, what is L, what is alpha, what is beta, what is plus, what is minus, how to open the cycle, and so much more. Without any further ado, let's dive into it. Carbohydrates, the simplest one, glucose, the most popular one, the most stable one, is an aldohexose because it contains 6 carbons. Aldo from aldehyde, the aldehyde group here. Carbohydrate because it's carbonyl group and it has a lot of hydroxy groups, that's why it's called hydrated. We have this way of drawing it. This way is the straight Fischer projection. Those pluses here in the middle represent the carbons, right? We have also fructose, we have also ketoses. For example, fructose, in this case, it contains a ketone group, right? These are the two cases of carbohydrates, simple ones, right? Okay, what you have to keep in mind here, for those groups that are horizontally in the Fischer projection, you have to assume that they come above the plane. Those groups that are above and at the end, you have to assume that those groups are behind the plane in order to assign the RS configuration. Okay, let's move further. Let's take a look at this simple example. Draw Fischer projection. In order to not make any mistake, you have to find the configuration for this compound as is given. So, if you remember, I did this video about these configurations, but here we are going to focus on the carbohydrates, but this is just an example to remember. So we have to arrange those groups to the from the highest priority to the lowest priority. In this case, OH has the highest priority. If you remember, the one who has the highest molecular mass has the highest priority. This trait connected with a carbon that is chiral. Okay, so this is going to be the first, this is going to be the second, and this is going to be the third group related with the priority, the highest priority to the hydroxy group, and the hydrogen fourth. Now the rotation is 1, 2, 3, and is clockwise. It looks like it's R, but indeed is not R, is S configuration, because this rule states in this way if the hydrogen is behind the plane. Hydrogen is above the plane because this wedged line represent above the plane. This dashed line represent behind the plane, and those straight lines like this represent on the plane, right? I know that this video is getting longer, but I have to add this information because it's going to get confusing later on this video. If the hydrogen is above the plane, you have to invert the configuration, right? Because the rule states that you have to keep that configuration clockwise or counterclockwise, R or S, if you have the hydrogen behind the plane. But if the hydrogen is above the plane, looks like you are watching on the other side, or you are looking on the other side, right? That's why you have to invert the configuration. Always, if the hydrogen is above the plane, invert the configuration, you are 100% right. Let's keep going with the editing now. Okay, now this is S. Now you have to draw the Fischer projection. Just make a plus, and it is advisable to place the hydrogen straight horizontally. Now arrange the groups on that way that you can reach the S configuration that you have here, because you are not allowed to change the configuration if it says straight draw the Fischer projection. Now let's assume this group here, this group here, and this group here. Now, first, second, third, right? Now, this is fourth. I said here previously that those groups that are at this position in Fischer projection, consider them like this. So remember the rule for hydrogen here? The same applies here. So you have a hydrogen above the plane. So if you count here 1, 2, 3, looks like it's R, but instead is S configuration for this carbon here, right? So hydrogen that is here is always above the plane, right? So rotation with 180 degree does not change the configuration. Rotation with 90 degree change the configuration. What this means, for example, if you rotate this group with this Fischer projection with 180 degree, means that hydrogen goes on this side, this group goes here, this group goes up, and this group goes down. Now you have again 1, 2, so 180, right? 2, 3. So 1, 2, 3 looks like R, but instead it's S because the hydrogen remains horizontal and is above the plane. Okay, rotation with 90 degree. If we rotate with 90 degree, we invert the configuration. Why? Let's try it now. So hydrogen will go up. And now what we have, this will go here by 90 degree. This will go here, and this will go here. What is going to happen now? First, second, and third. First, second, third. It's R, but hydrogen at this position is behind the plane, right? According to Fischer projection. So the configuration goes R. So we do not want that. Be careful. Okay, hope it was clear, this one. Now let's move to sugars. DL sugars. For historical reasons, right? D represent dexa-rotatory and L levorotatory in terms of rotating the polarized light, but it does not correspond all the time. In case of sugars, does not relate with the rotation of the direction of the polarized light. I mentioned also here. What D means? D means that the lowest chiral center at the sugar is at the right side. So this is the lowest chiral center. The OH, this OH here has to be at the right side, right? If it is L, this OH here has to be on the left side, right? Only the lowest possible chiral center, not all the groups. Keep in mind this. D right side, L left side. In this case is D arabinose, so in this case is D sugar and is on the right side. D represent R stereochemistry for the lowest chiral center, L represent S stereochemistry for the lowest chiral center, but I recommend always to check. Only system only for one chiral center. Okay. Plus and minus now represent straight the clockwise and counterclockwise rotation of plane of polarized light. Okay. Let's move further. Assign RS configuration to each chiral center and tell if it's D or L sugar. This is xylose. If it's, let's start from the easiest one. Is D or L? So in this case, the lowest chiral center is this carbon here, and the OH is on the right side when you look at the sugar, and this is going to be D xylose. Now, in terms of RS, let's start from like 1, 2, 3, 4, 5. Now, this is not chiral. This is not chiral because it does not contain 4 different groups. It does not contain 4 different groups. The second one, yes. So who has the highest priority here? OH. Second, who comes? Comes this carbon here, because this carbon here is connected like this. So it's like carbon oxygen and carbon oxygen, if you remember, right? But this carbon here is connected with one oxygen and another carbon. So this is the highest priority, and the groups below stands for the third position. So third. This is going to be fourth, because the hydrogen is above the plane. Now we have to invert the configuration that we find. So first, second, third. So first, second, third means S straight, but because hydrogen is above the plane, this is going to be our configuration. Right? Let's move further. This carbon here, third position. First group is this one. Second group is going to be this carbon here or this carbon here. This carbon here is connected with one hydrogen, one oxygen, and one carbon. This carbon here is connected with one oxygen, one hydrogen, and one carbon. But we have to move further in case you do not find the answer at the lowest possible carbon. So if we move further, this carbon here is connected with two oxygen. This carbon here is connected with only one oxygen, and the others are hydrogen. Oxygen has higher atomic mass compared to hydrogen, so has the highest priority. So it's going to be first, second, and third. So first, second, and third rotation looks like it's R, but instead is S because the hydrogen is above the plane, right? And the fourth one, first. Now, second is going to be this one because it's connected with one oxygen and another carbon, but this one here is connected only with one oxygen and hydrogens. So it's going to be first, second, third. First, second, third looks like it's S because hydrogen is above the plane. It's going to be R. Right? Hope it is clear. In terms of stereoisomers, is this simple formula that we have learned at this video. To n equal to maximum number of stereoisomers. N is number of chiral centers. We have 1, 2, 3 chiral centers. 2 to power 3 means maximum 8 possible stereoisomers. Right? But we are not going to draw that. Look at this video if you want to know how to draw all stereoisomers. Let's move further. Okay, something to clarify. Here, this is the cyclohexane. It's not a sugar, but we have to remember something because we are going to move to cyclization of sugars. Here is a plane, and you are here above the plane and below the plane, above them and below the plane. Now, if this position here is axial, if you do ring flip, it's like stretching this part here down here, that is this part here, and this part here up here, right? So this axial position is going to move to equatorial position. So it's going to stay again up, but here, right? Now, here, do not confuse some things. If you are considering cis and trans, do not mess with equatorial or axial position. What I mean with this, for example, if I add also something here, those two, this is up and this is up and are in cis. But if you consider this one, for example, with this one here, this is up and this is down, I draw this line like this because it has to be parallel with these two lines, right? Keep in mind this thing. This is down and this is up. This is equatorial, this is axial. But those two, it doesn't matter if they are in equatorial and axial, but those two are in trans position. For example, take a look at this one. Those two, this one and this one, are both in equatorial position. But according to cis and trans, those are trans, right? Up the plane, down the plane. Imagine a flat plane on this chair-like conformation, okay? Now, this is up, this goes up again here. It changed the position from axial to equatorial, but does not change the side. Keep in mind this thing, okay? This is up here, and this is going to stay up also here. So, I hope you get the idea. If it's in axial, if you do ring flip, it's going to be in equatorial. If it's in equatorial, if you do ring flip, it's going to be in axial. But it's going to keep the same position. Hope that this is clear, because it's important what's coming above, what's coming below. Okay. Cyclization of monosaccharides. If you remember, I mentioned in one of my previous videos, but no need to remember. You react an aldehyde with an alcohol in presence of acid catalyzed, you yield this compound that is an hemiacetal, right? Hydroxy, and looks like an ester, but is called an hemiacetal because it has a hydrogen here. If a carbonyl or hydroxyl group are present in the same molecule, An intramolecular nucleophilic addition takes place by forming a cyclic homoacetal. This is the idea of cyclization of the sugars, because you have aldehyde group or ketone group, and you have also the hydroxy group on the same molecule. Okay. So let's move to a simple example. D-glucose, D because OH is on the right side. Now, in order to do cyclization, you have to keep in mind that the most commonly ones are pyranose form and furanose form. Furanose with 5 elements, with 5 atoms, pyranose with 6 atoms. Cycle. Okay, pyranose form from pyran. Okay, just to keep in mind. Now, in order to do cyclization, you have to keep in mind that you're going to have, in case of glucose, D-glucose, a connection between the lowest hydroxy group that is directly connected with the chiral carbon, the lowest possible chiral carbon, with this aldehyde group to form cyclohemiacetals. The problem here is that you can have the formation of a new hydroxy that can be formed on this side and on this side. To a certain percentage, depends on stability, but you have the formation in both sides, and those forms are called anomeric forms. We have alpha and beta anomers. Alpha anomer is in the case that this OH that is newly formed is cis compared to the lowest possible hydroxy group that is connected with the lowest possible chiral center. So in this case, this is a D sugar and has an OH on the right side. And this hydroxy is on the right side, the same as this OH to the lowest possible chiral carbon. This is going to be called an alpha anomer. In the case that they are trans, this OH that was here with this hydroxy here, they are going to be called beta anomer. Be careful what I am saying in this way, because if in case you have an L sugar, it's going to be on this side OH, and this in this case is going to be the beta anomer, and this in this case is going to be the alpha. Alpha cis, beta trans, related with the newly hydroxy group format with the hydroxy group to the lowest possible chiral carbon. Right? Clear this one. Let's move further. Now, let's do, for example, the first one, that was the alpha anomer. By convention, the oxygen is on the right side here, up. Right now, when you start numbering and placing the OH group to the cycle, you have to keep in mind one rule. All the groups that are on the right side are going to be down. All the groups that are on the left side are going to be up. What I explained above with that cyclohexane, right, is not related with cis and trans. Up and down with a horizontal plane. Keep in mind, this thing is so important. What is on the right side is going to be down. What is on the left side is going to be up. Now, for D sugars, the last thing that I'm going to say is that this CH2O is going to be up. For L sugars, this is going to be down. Okay, let's write for the D sugars first. Now, starting numbering, this is the one that is forming the bond. Now we are going to start from the first one here. So first, second, third, fourth, and fifth. Now we are writing the alpha. Alpha D gluco pyranose. Right? So because this is on the right side, this is going to be down. The second one is again on the right side. I mean right side when you look straight to the sugar, right? So this is going to be down, and because those two lines are parallel on this way, you're going to write it on this way. Third sugar is going to be on the left side, it's going to be up. Fourth sugar is going to be down. Fifth, now you have this one. For D sugars, it's going to be up. Right? Let's write now the beta anomer of the D-glucose. Now, in this case, this is on the left side. The hydroxy is going to be up. I suggest, as a beginner, write numbers. Is not a mistake. Do not get confused. Now, the second one is on the right side. It's going to be down. The third one is going to be up. The fourth one is going to be down. The fifth one is this group here. That's because it's D sugar, it's going to be up. If it's L sugar, it's going to be down. Right? Now, the idea of this up and down, but remember D up and L down, is that this group is skip. Okay. So that is beta D-glucopyranose. Now here arises a question. Who is more stable, alpha or beta? Related to, you have to remember, if you watch that video, this video here, that when we did the stability of cyclohexane, we said that the more groups you have in equatorial position, the more stable is the compound. In this case, in beta D-glucopyranose, you have all the groups in equatorial position, but in alpha 1 you have one group in axial position. So this is going to be the most stable between these two. Okay? Hope it was a little clear. Let's move further. Now let's move to ketose. Write alpha D fructopyranose and alpha D fructofuranose. Furanose means 5 elements to the cycle. Okay, now the idea here is that you connect this oxygen to this carbon here, or this oxygen to this carbon here. In case of this 6 carbon here, it's going to be 1, 2, 3, 4, 5, and the oxygen is going to be 6. So in this case, it's going to be pyranose form. In case you connect those two, it's going to be 1, 2, 3, 4, 5. It's going to be furanose form, name from this compound. Okay, let's do first pyranose form. So in this case, I am placing the oxygen here. I could place also the oxygen here, but for those ketoses, books generally place the oxygen here, but it's the same. So the first position, because it's alpha, you have to keep in mind that the OH that is going to be formed here is going to be cis with the OH that is at the lowest possible chiral carbon. So it's gonna be on this side, because this is a D fructose, is on this side, and in this side we said that it's gonna be what? Up and down. Right side down, left side up. Okay? So in this case it's gonna be down, but you have this group here that remains up, because the numbering starts from this one, right? It's a little confusing, but not as much. 3, 4, 5, 6. So at the third position, you have an OH on the left side, so it's gonna be up. Fourth position is gonna be down. Keep in mind, it has to be parallel, this line, with those two. Fifth position is going to be down, and what remains here, it remains this carbon with those two hydrogens, because here you have the connection, right? Okay, this is the alpha D fructopyranose. Let's write alpha D fructofuranose. In this case, the cycle is like this. Now, the numbering starts from here. Be careful, it is saying alpha, okay? Alpha means that again the OH is on this side and is connected with this OH here. It doesn't matter for alpha and beta anomers because you did the connection for this first one with this OH here. You have, for alpha, you have to keep in mind the lowest possible chiral center as a determining factor. So if this is D on this side and this is the formation is on this side, cis to this one of the newly OH, it's going to be alpha. It doesn't matter if you connect it here. So if it's on this side, it's going to be down. Okay, in this case, it's again alpha and it's going to be down. So the OH here is going to be down. And this is going to remain up. So 1, 2, 3, 4, 5. Now, at the third position, you have an OH that is up. At fourth position, you have an OH that is down. Fifth position, you have an OH that is down. And now you have this group that remains here that's going to remain up. Right? Okay, hope is going to be a little clear. Don't worry, more examples on the way, keep watching. This example was requested from one of my students. Write the structure of beta-D monopuranos by knowing that is epimer in C2 with D-glucose. Now, what means epimer first? Epimer means that it changed only to that carbon. So in this case, C2 is this carbon here. Only here, because this is D-glucose, only here is the change. Okay, so this group has to move here, and this group has, this hydrogen is going to move here. So let's draw D-manos first. So one, two, right? Now, the exercise wants to write the beta structure. In order to be beta, the connection here is going to form an OH that is going to be trans with this OH that is at the lowest possible chiral center. So let's write the Puranos cycle. Okay? Now, because it's beta, this OH that is going to be formed here means that it's going to be trans to this one. It's going to be on this side. Trans to this one, I mean, right? So if it's on the left side, it's going to be up. So let's place a number 1, 2, 3, 4, 5. Now let's move further. Second is going to be on the left side, it's going to be up. Third position, up. Fourth, down. Fifth position now, because it's D, it's gonna be up, right? That is the solution for this exercise. Let's move further. Now let's write open chain from the sugars below. Now let's do the reverse. I know that you got a little tired, but anyway, let's keep ending also this last one. And after this, you're going to have a homework if you understood what we were doing up until now. Now, let's draw the Fischer projection. Now, this is an aldose. This is a ketose. This is an aldose. How do I understand that it's an aldose? Because I do not have to this oxygen, the first carbon here connected with this, with another carbon branch, like in this case. And even here, I do not have it, right? Okay. Now, CHO. So let's place numbers. This is going to be first, second, third, fourth, fifth, and sixth. Now, this first one is what? Because it's up, and this is up. This is up. Remind us that we are dealing with a D sugar, right? Up, D, down, L sugar, keep in mind. Okay, let's move further now. What we have at the second position now, this is up. So up means left side, hydrogen on this side. First, second, third, fourth, fifth, and sixth, that is going to be this one. Now, for the third position, this is down, means that this is going to be here. And this is hydrogen. For the fourth position, this is down, it's going to be here. I mean for this one. And for fifth position, because this is up, this means that it's a D sugar, and it's going to be on the right side, right? Let's move further to this one here. So we understood that it's a ketose, so straight we can write this one, right? Now what we have, 1, 2, 3, 4, 5, and 6th one is going to be this one. Now let's place number 1, 2, 3, 4, 5. Now for these two here, first we understand that this is a D sugar, right? Because this is up. Secondly, at this position 2 is this OH that is formed here, that in this case is in, because this is D, and the OH here is gonna be on the left, on the right side, sorry, and this is going to be down here. This means that this was alpha sugar, because it's cis. Down means this side, and it's in cis with this lowest chiral center here. Okay, so we skip this one because we do not need that to write the Fischer projection. Let's move to the third position, because 1, 2, 3, 4, 5, 6. Third position, what do we have? An OH that is up. Fourth position, an OH that is down. And the hydrogen here. And that's it done. Let's move to the last one. We understood that is a aldehyde, aldoketose. So at the end here is going to be CH2OH. So 1, 2, 3, 4, 5, right? Now, for the first one here, this is the one that is the anomeric hydroxy group. Is this an alpha or beta? Keep in mind, this is down, which means that this sugar here has to be L sugar. This is up, this is up, and this is up. What this means? This means that this is an alpha sugar. This has been an alpha sugar, right? Because it's in cis. Up, up. Here what we had, down, down for this one here. So what we have, first, second, third, fourth, and fifth. So for the second, what we have? For the second we have this one here that is down, it's on this side. For the third is down, and hydrogen, and for fourth is up, and because this is down means that this is an L sugar, and this has to be on the left side, right? Okay, a lot of confusion. Anyway, hope you understood, and this is your homework. Find this sugar. Is a furanose or pyranose? Is an alpha or beta? Is a D or L? Write them in the comments down below. Or L. I will keep looking if you find it right. Okay, hope you find this video helpful, and look forward to see you to the next video that is with the reaction of the carbohydrates. Up until there,